I take over. So it's 4:30 p.m. here in Central Europe. Good afternoon, everyone, to the second lecture of Pablo Jarillo Herrero. Yesterday we got a very nice pedagogical introduction into the wonderful world of twisted angle bilayers of graphene, and today we will hear more about this. Pablo, let's twist again.
Okay, very good. So thank you everyone for joining again for this second lecture on Magic Angle Graphene. And as promised, I have a virtual background which is now less huge, okay? And hopefully sometime in the future we can all be there for real. So I want to start by just reminding you all of the basics of Magic Angle Graphene in the first couple of minutes, just in case there are people who didn't join yesterday for the lecture. So one thing that, as I mentioned yesterday, has become clear is that Magic Angle Graphene and the field in general of correlated Moiré heterostructures is leading to the merging of modern condensed matter communities which did not interact that closely, as closely before. One is, of course, the 2D van der Waals materials and heterostructures community, people that investigated graphene, transition method like chalcogenides, etc. Then, on the other hand, there are the people who work on strongly correlated materials, pnictides, cuprates, organic superconductors, etc. And then the people that work on topological condensed matter physics, quantum Hall physics, fractional quantum Hall physics, topological insulators, etc. So all these three come together in the field of correlated Moiré heterostructures. And today I want to go and advance a little bit more. So just to remind everybody, if you have two sheets of graphene stacked on top of each other within a single particle picture and without interactions between hybrid, tunneling between the layers, this is what you get, two Dirac cones that interpenetrate each other. The separation between these Dirac points is proportional to the angle of rotation for small angles. If you count interlayer hybridization, okay, then in reality, because the electrons can tunnel between the two sheets because they're only 3 angstroms apart, then a gap opens here. This is the situation when the interlayer hybridization is much smaller than the energy of this crossing point. Yeah? But as you twist, as you decrease the twist angle, this gap goes lower and lower and lower until the bottom part leads to a flat band condition. And that flat band condition is reached at the magic angle, which is about 1.1 degrees. And this was, this magic angle was coined by Bistros and McDonald, and there were earlier STM works and also some other calculations predicting the existence of these flat bands, as I mentioned yesterday in more detail. Now, again, let me just run this video. This video shows what is the evolution of the electronic structure. This is a cartoon, so the evolution of the electronic structure as you rotate the angle from 3 degrees towards the magic angle. Okay, what you can see is that within this energy window, as you go below about 2 degrees, there's a major reconstruction with this set of bands separated by band gaps. These bands become flat at 1.1 degree there, and then there is a more complex evolution. Okay. Now, including lattice relaxation, this number may vary a little bit above and below, but the basic thing is that you have these flat bands. And then after that, I mentioned yesterday that, when we fabricated our first devices at the magic angle, between two graphene sheets, we noticed that there are this existence of these correlated insulator states when you put 2 electrons or 2 holes per more unit cell, and then superconductivity when you dope with extra electrons or holes nearby that correlated insulated state, okay? And this was the subject of yesterday's lecture. So I want to go back, a little bit to the basics and, so that we can go deeper. So this is the phase diagram, temperature versus density for graphene and also for large angle twisted bilayer graphene, okay? There is only one, the electronic structure is just these Dirac cones, and there's only one interesting point. That's the charge neutrality, often also called the Dirac point, okay? On both sides of this is a metal. At charge neutrality, the behavior is a little bit more, charge neutrality, you're in a semi-metallic behavior, but graphene conducts everywhere in this phase diagram. Now, what happens if we have twisted bilayer graphene of a small angle? And this is the phase diagram, this is temperature, and now I'm substituting here, rather than just density, I'm normalizing, and I'm calling this filling, okay? Filling factor nu. This is now how many electrons or holes I'm adding to the system from charge neutrality compared to the 4 electrons or 4 holes, compared to the per Moiré unit cell, okay? So 1, 2, 3, 4 means 1 electron, 2 electron, 3 electron, 4 electrons per Moiré unit cell, and the thing -1, -2, -3, -4 means -1, 2, 3, 4 holes per Moiré unit cell. Okay? Now, as you remember from yesterday, this time, because we have this set of bands, okay, separated from band gaps from the remote bands. These are now Moiré bands, and this is the closest to charge neutrality set of Moiré bands. And then you have these other, sometimes we call them remote bands. There is a separation of a band gap here. So you see, to fill from charge neutrality all the way up to the band gap, we need 4 electrons per Moiré unit cell. So when you reach that point, okay, you reach a band gap, so you have a band insulator once you fill 4 electrons per Moiré unit cell. The same thing if you fill with 4 holes, if you empty completely this band and you have 4 holes per Moiré unit cell, you also have a band insulator. And then you have also the charge neutrality point and metallic behavior in between. Okay, this is for large angle, sorry, for small angle twisted bilayer graphene, but not yet magic. Now, if you go to magic angle graphene, okay, this is the phase diagram, and this is sort of schematic as of mid-2018, okay? You have, again, you have this set of flat bands with large band gaps separating from the other more remote bands. So you have also a band insulator states, single particle band insulator states at 4 electrons and 4 holes per Moiré unit cell. You have the charge neutrality point, but at 2 holes per Moiré unit cell, or at 2 holes per Moiré unit cell, or at 2 electrons per Moiré unit cell, you have a correlated insulator. And when you dope, you have superconducting domes when you dope around from it. Okay. Now this is schematic. Don't pay too much attention to the details. Do these overlap or not? Are there 2 domes or 1 dome on either side here? These are sort of details that can be sometimes sample dependent, but this is sort of schematic what happens. And then, as of now, okay, and again, schematic, it's angle dependent, twist angle dependent, and it's evolving fast, okay, with experiments, happening every other week or every month. We have the following. We have realized that there is a region of strange metal behavior, linear in temperature resistivity, okay, around the correlated insulated states. And this is very reminiscent of the strange metal behavior in many correlated materials. Whereas, for example, near charge neutrality, you have regular metallic behavior. The superconducting state exhibits anisotropies, which lead us to conclude that there is a nematic superconducting state. There are a series of, this competition between different orders near, along the superconducting state. And there are also regions of nematicity in the normal state. Okay, these are things which I'm going to be telling you about today. Now, in addition, and I'm not going to speak much or at all about them today, but in addition, we have a lot of other interesting physics which is happening at fillings of 1 and 3 electrons or holes per Moiré unit cell. Okay, and all of this physics, has been seen by a number of groups. I'm only listing here a partial list of references, and there's a lot of interesting recent STM work also, as I mentioned yesterday. Now, one of the things that I want to mention that I also briefly mentioned yesterday is that, by now, as we measure many, many, many more devices, we're starting to gather statistics about how these systems, work. For example, now we can map what is the optimal doping TC versus twist angle for different samples, okay? And I put it here about, over a dozen samples. These 2 green data points at the bottom have a lot of twist angle disorders, so it's very the determination of the twist angle is not very clear, so don't pay too much attention to them. For the rest of the data points, you can see that there seems to be sort of a dome of TC versus twist angle, okay? With, the lowest twist angle for which we have measured superconductivity is about 0.95 degrees, the maximum about 1.2 degrees. And other groups have, similar boundaries, maybe a group has seen a slightly lower twist angle superconductivity also, maybe a little bit higher. Now, this, reminds me, to tell you about something which the community is still trying to figure out, and it is, what should we call magic angle graphene and what are the implications, okay? Now, one option is to use the original definition of McDonald and Bistritzer. Let's say we will call the magic angle, the twist angle for which the Fermi velocity is 0 or minimum at the K points. Okay, as you rotate the twist angle at the K points, the velocity goes down, goes down, goes down. At some point it reaches 0 or its minimum. We call that magic angle. Now, that's not the only possible definition. You could also say, well, option 2 is the angle for which the bandwidth of the flat bands is minimum, okay? And it does not happen for the same angle as option 1, okay? But since what we care for in terms of interactions is that the bandwidth is small compared to the interaction energy, then maybe it makes more sense to call magic angle the angle for which the bandwidth is minimum. And yet another option is the angle for which the density of states, in particular the von Hooft singularities associated with the flat bands, is strongest or narrowest, okay? So not the angle for which the whole bandwidth is minimum, but the angle for which locally in the band structure you have the flattest band structure at a given energy, locally in momentum space and energy, okay? This approach has been, for example, suggested by the Columbia group working on STM and Magic Angle Graphene. Okay? Now, whichever definition you want to take, as of now, it is yet unclear how do these relate to the magic, the experimental magic, if you want, which is the presence of correlated insulator behaviors and superconductivities. And in particular, we don't know which of these, if any of them, definitions leads to the strongest correlated insulator states, and for what filling, because different fillings have different strengths of the correlated insulator state, and what of these options leads to the highest TC, and again for what filling, because there are different superconducting domes in different regions of the phase diagram. Okay, so all of this basically connecting theory to experiment is still under development very much, and we don't know yet what controls what exactly. Okay, and there may be an interplay between different things. So this is one thing that I wanted to tell you about. Then, so the outline for the rest of my talk today is the following. I'm going to start by telling you about competing orders in magic angle twisted bilayer graphene, then about the presence of nematicity. Then I will tell you about our recent experiments with the group of Shahali Lani at the Weizmann Institute on measuring a cascade of phase transitions and Dirac revivals in magic angle graphene. And then I hope to have time to tell you at the end about our observation of strange metal behavior in magic angle graphene. Okay, but please feel free to ask any questions, and you can ask them during the talk, at the end, and I don't need to necessarily cover all. I'll be happy to cover all, but I wouldn't need to cover everything. The most important thing is that you understand, the basic message of what I'm telling you about. Okay, so competing orders. So this term competing orders, and often also a related term intertwined orders, is a term which has been used in a number of correlated materials, but perhaps with the most significant case, that of the Cuprates. Yeah. So here's the phase diagram, temperature versus hole doping, okay, for Cuprate superconductors. It's taken out of this famous review. And as you can see, the superconducting dome, okay, is not a single dome, okay? You can see that it's more like a camelback. It has two domes. Okay, in particular, there's this region where there is sort of this inflection, point, where there is a depletion of TC, of the superconducting TC around this 1/8 doping. Okay, you can see that in this phase diagram there are different phases, and in particular there are some phases which seem to be intertwined with each other, meaning some orders which are present. Okay, and in some cases they seem to compete like this. Okay, the presence of this dip in TC, rather than just a dome that you would have expected, continuing like this depletion of TC has been attributed to the presence of charge order in cuprates. For some cuprates, like lanthanum barium copper oxide, this depression of TC can be almost all the way to 0 at this 1/8 doping. Okay. So now let me show you what we measure in Magic Angle Graphene. So this is a high temperature, okay, higher temperature than I was showing typically yesterday, phase diagram in Magic Angle Graphene. This is for a device with a twist angle of 1.09 degrees. Okay. Now this is temperature up to 20 Kelvin. This is density. This is charge neutrality. As you can see, we have correlated insulated states at 1, or correlated semi-metallic or insulated states at 1, 2, and 3 electrons per mole unit cell. For holes, something happens around -2. Okay, this is density. This is not filling factor. Okay, this is density of electron. This corresponds to -2 holes per mole. So 2 holes per mole unit cell. There is a superconducting dome. Let me focus a bit in this region. Okay, but this is, as you can see, this is by any standard, this is a very high quality transport device. Okay, with lots of correlated states and superconductivity. So if I zoom in into this region a little bit, okay, you see that we have, this is our correlated insulated state that happens at low temperatures, okay, at 2 holes per mole unit cell. And now you can see that there is some feature that comes from relatively high temperature. Okay, we sometimes call it the banana, because in this color scheme, it looks like this yellow, a little bit bent thin. So you can see that there is that feature, and that feature goes down there, and it seems to create a depletion in the superconducting dome, which is this dark blue thing. Okay? Again, let me zoom in a bit more. Okay, so here is a further zoom in this region. So this is filling factor now. Okay, here I put hole doping. So 2 holes per mole unit cell means 0 doping when you want to compare the cuprates. Now we go to 2 holes plus extra holes. So filling factor -2 minus delta, okay, which is equivalent to hole doping. Okay, and you can see that there is indeed that feature there. Okay, this is again very reminiscent of this. Okay, remember here you hold up in this direction, here you hold up towards the left. Okay, so you see that this is actually a theoretical phase diagram, but we're measuring this continuously. This is actual data. Okay, you can see the shape of the superconducting dome with a depletion in that region. Yeah. So now, when we look at this, we were like, what is that thing? It seems like there is something here that wants to compete with superconductivity and creates a depletion there. Why don't we suppress superconductivity, for example, by applying a small magnetic field, small perpendicular magnetic field, and let's see what's really underneath there. Okay, so we did that. We take this exact same device, we just apply a small perpendicular magnetic field, and what we see is the following. Okay, this region that had this depletion here leads to an insulating state at low temperature once you suppress superconductivity. So let me show you these traces just to make it more apparent. Okay, at 0 magnetic field, you have the resistivity goes down and the system becomes superconducting. At a small finite magnetic field, resistance goes down and becomes an insulator at the exact same doping, at the exact same density. Okay, so we saw it once and we weren't sure if this was a generic feature or not, but then you see it again and you see it again, particularly in samples within a specific angular range. So This is another example. This is sample M6, 107 degrees plus minus 103 degrees. You have, again, this high temperature feature, this banana it's called here. The correlated insulated state at nu equals -2 is very, very weak, actually. Okay, this creates a depletion there in TC. If you apply a small perpendicular magnetic field, you can see that this high resistance rich goes into an insulating state next to, but not exactly, at about 10% doping from the correlated insulated state at filling factor -2. Okay, and again, if you take a trace there, you can see that in one case you go superconducting, in the other case you go insulated when you have a finite magnetic field applied. So now you can do this actually continuously. Okay, so you can measure TC. Okay, these are measurements of TC versus hole doping at different magnetic fields. Okay, yeah, and the magnetic field is varying continuously. Here I'm showing just particular traces at different values here. And what you can see is that at some finite magnetic field, you split the superconducting dome into two domes. Okay, and then you suppress the smaller part. Okay, and then you remain only with one dome. This is very similar, again, very reminiscent of data in the Cuprates. This is a paper by Brad Ramshaw, where they measure TC as a function of hole doping and magnetic fields. And then at some point, you can see they split the superconducting dome into two domes, and then only one of them remains, okay? Of course, the difference, again, between this and this is that the continuous lines that you see are, guides to the eye. In reality, there are only a few dots, as you can see here, okay? Whereas this is actually a continuous measurement. So let me leave that there. I'm going to return to it, okay? But let me leave that there. There seems to be some competition between, orders that leads to a depletion of TC, within superconducting dome in Magic Angle Graphene at a doping of order 10%, from the correlated insulator state. So now let me tell you about nematicity. So nematicity means spontaneous breaking of lattice rotational symmetry of an ordered parameter, okay? Many families of quantum materials show this: the pnictides, the cuprates, heavily doped topological insulators, which are also superconductors. Nematicity can happen in the normal state, in the superconducting state, or in both. And it has different implications in each case. Okay? Here I'm showing on the left a typical phase diagram of the pnictides. This is taken out of a review by Rafael Fernandez and collaborators. And you can see that the pnictides is perhaps the system where nematicity has been investigated the most. Okay, and you can see that here in that temperature versus doping, you have this phase here, this nematic region where you have in the normal state nematicity, okay, and the region above it has nematic fluctuations, etc. Okay, now in doped topological insulators, okay, for example, I think copper dope or strontium doped, and you can dope topological insulators such as between selenide with several materials. They become superconductors, and people have seen that when they look, for example, at these cases, TC versus magnetic field direction, okay, they can see that there are two maxima within 360 degrees. Okay, this is the same as this, so two maxima, which means that the system goes from a crystal symmetry where you have threefold rotational symmetry to a response which is twofold symmetric, has C2 symmetry, meaning ellipse, okay? An ellipse or a peanut, this has one axis of symmetry. That means that the system has chosen a direction, okay? Before, the natural crystal symmetry, okay? The rotational symmetry of the crystal is threefold. It's a hexagonal system, and the system chooses a given direction, okay? Some order parameter chooses a given direction, and therefore it exhibits C2 symmetry, an ellipse or a peanut, okay? Sorry. So this is what the evidence for nematicity is, for example, in this system. Now, let me tell you what, about our experiments. So this is and again, you can look at this in the, this paper is posted on the archive. So this is a Magic Angle Graphene device, okay? It's where we are able, we cool it down in a cryostat where we're able to apply an in-plane magnetic field and vary the magnitude and the direction of the in-plane magnetic field, okay? This is done with a vector magnet. Now, this is one of our highest TC samples, 3 Kelvin, as measured by 50% normal state resistance, okay? With beautiful switching currents, beautiful superconducting curves, okay? Now, if you measure the resistivity as a function of magnetic field direction angle in plane, okay, parallel to the graphene, Magic Angle Graphene plane, we see these two maxima, okay? This means that the system is exhibiting C2 symmetry. It's exhibiting a response with the shape of an ellipse, okay? The system chooses a direction, okay? Now we can do this at different dopings, given by these letters, A, B, C, D, E, F, G, H, I, etc. Okay, let me show you in the next slide. So as I told you, the response of the system is an ellipse. And here you have the ellipse, okay? If you plot it in polar, coordinates, Rxx versus Vx and Vy, what you can see is, this blue region means it's superconducting. So the system has a much higher in-plane critical field along, this direction than in this direction, okay? This direction, the system goes from blue to red. So the critical field is below 1 Tesla. Here, it actually is larger than 1 Tesla. So it's blue all the way to the edge, okay? Now we can do this at different dopings, okay? And we can do this at different temperatures, etc. So one thing that it's nice, okay, so because we have a limited magnetic field magnitude for our vector magnet, we can only run up to 1 Tesla, okay, in plane. This means that we, have to choose sometimes intermediate temperatures in order to determine the orientation of the ellipse. For example, at optimal doping, if you measure even at 0.9 Kelvin, it's always, point D is optimal doping, it's always superconducting because the critical field is above 1 Tesla in any direction, okay? But for example, at optimal doping, if you go at 2.4 Kelvin, okay, so even at 1.7 Kelvin, you can see we cannot see the ellipse, but if you increase the temperature to 2.4 Kelvin, now we can see the ellipse, okay? So at base temperature, we have to choose a doping where we have, very low TCs so that we can measure these ellipses, okay? And at the intermediate temperatures, we can see an ellipse over a variety of dopings like here, okay? So again, we have detailed data in this paper at all dopings, all temperatures, etc. And I encourage you to have a look at it. The thing that I want to draw your attention to is the following. The major axis of the ellipse changes direction as a function of doping, okay? So remember, all these A, B, C, D, E, F, etc. are points here in these dopings. And what you can see is that, for example, for E, we have the major axis of the ellipse is at about, I don't know, something like 45 degrees. Then you go to K or you go to H, and the ellipse has rotated, okay? The axis is minus 30 degrees or something like that, okay? So this is very important because, you might wonder, okay, we're measuring the anisotropic behavior of the critical parallel field, but maybe what happens is that your system has a very strong strain, and the strain is what is selecting a particular direction, okay? So this is not spontaneous, symmetry breaking, but has to do with you have a very strong strain, and of course you have a response which is symmetric with respect to the strain axis, okay? But of course, strain is not going to depend for a given sample on how many electrons we put in the sample over very small density changes of electrons. So the fact that this major axis ellipse of the ellipse is rotating with density indicates that it is very likely of electronic origin. Okay, this is not something which is associated with a very strong, strain that is spinning the direction of the ellipse. So we also have measured. So here we're measuring the critical magnetic field, for which we take the system out of the superconducting state by a magnetic field, right? You can do an alternative, and for that sometimes we need to increase the temperature.
Can I ask you,
Sure.
in which direction is the current flowing?
Yep. So we have measured this, and it is independent of the direction that the current flows. Okay. We have devices where we have the current, we can flow it along one direction or along the perpendicular direction, and the ellipse is always in the same direction at a particular doping.
Okay.
So, okay. So I was saying that we can measure these ellipses in the critical field. Okay. But for that, sometimes you have to bring the system to relatively high temperature. You have to bring it out of the superconducting state by applying a large magnetic field. We can do an alternative measurement, which is we can keep the system at low magnetic fields and at low temperature, always at base temperature, but now run a large current. So we can measure if the critical current has also any anisotropies. And indeed, they do have it. Okay, I'm going to run a video now. The video is going to contain too much information to you to fully capture in this, in this short lecture. I just want to give you a flavor, and I'll show you some particular traces in a moment. But I'm going to run a video. You see different panels here. These different panels, they represent the vertical axis is angle, okay, of the magnetic field direction, angle. The horizontal axis is current bias. So we're biasing our Magic Angle Graphene with a given current that it increases. And then different panels have different values of the parallel magnetic field, the magnitude of the parallel magnetic field. The direction, again, is given on the vertical axis. And the video that I'm going to run goes through different densities. So again, we have so many knobs in this system, that we have to take these, multi-dimensional space plots and show them as videos. Let me just run this, okay? So as you can see, as we vary the density for certain regions, you have these anisotropic responses, okay? Let me just run it again. See, now you see there anisotropic responses. Let me take a trace out of, oh, sorry, let me go, stop it. Let me, take a snapshot at one particular density, okay? You can see here that for this particular density and at different parallel magnetic fields, you can see, for example, here that the system, okay, at 0.8 Tesla parallel magnetic field as a function of rotation angle, for some angles, the system is superconducting, and for some angles, the system is actually insulated. It has a peak in the differential resistance at zero bias, okay? And of course, there are two of these, two maxima, two minima, so this is an ellipse, okay? So let me show you actual traces, which may be simpler for some of you to interpret. This is the differential resistance as a function of current bias, okay? Shown only for positive values here. You can see that, and the different color traces are the different angles, okay, of the magnetic field in steps of 15 degrees. You can see that there is this switching current. Okay, the system here has zero differential resistance, and then it switches, okay? So out of the superconducting state, this switching current evolves with twist angle. It has two maxima, so this has C2 symmetry, okay? Now, I'm sure all of you are noticing that there is a second sort of switching event here, okay? And this switching event, actually, if you pay attention, has a phase shift, in the sense of a angular shift with respect to this one, okay? It's about, when this thing is maximum, the maximum on the second switch occurs about, something like, I don't remember exactly, 90, 60, either 60 or 120 degrees approximately, okay? It's not precise, later, okay? Now, this tells us again, okay, I don't want to comment too much about this. This could be due to different, nematic domains, etc. But both the critical parallel magnetic field and the behavior of the critical current versus parallel magnetic field tells us that the system, the superconducting state, exhibits an anisotropic response, and in particular, a C2 symmetric response. The system chooses a given direction, okay? Now, that's for the superconducting state. What about the normal state, okay? And now I'm going to make a connection back to the previous part of the talk, the competing orders part of the talk. So this is the resistivity, temperature and density for one of these devices where we have a dip in the TC here, okay? Now, let me measure, this is a whole bar device, okay? Let me measure the transverse RXY, the transverse component of the resistivity at zero magnetic field, okay? In principle, because I'm at zero magnetic field, if the system is isotropic, I should measure zero resistivity, but zero transverse resistivity. But look at, oh, sorry, and by the way, just to remind you, this is this banana feature, this depletion in TC, this is the correlated insulator state for holes. This is what this hole, it's not really hole because it's zero magnetic field, it's transverse resistance, RXY, measurement leads to, okay? You can see that, and I'm just placing now this white line without any adjustments on top of this diagram. You can see that in the region where we have this maximum, this resistance maximum here, which leads to the competition with the superconducting state near zero temperature, in that same region, we measure a finite transverse resistance, okay? Whereas everywhere else, the transverse resistance is almost zero, okay? Here you see there's almost no signal. Here there's little signal, but here there's this big, look for deep dark colors, right? This is dark blue. So now, how is that possible that you measure the finite resistance? Well, let's imagine you have an anisotropic system, a system where the resistivity is a tensor, and you have different resistivity along direction 1 and along direction 2. Now, if you're doing a measurement in a whole bar geometry, where the X and Y axis, okay, the axis of your device are parallel to your anisotropy axis, the X component is the 1 axis, the Y axis is the 2 axis, then you measure indeed at zero magnetic field, even in the presence of this anisotropy, zero transverse resistance. However, if you have a device where your device axes are at some angle with respect to your anisotropy axis, okay? If there's a rotation angle between the two, you need to do a transformation of your resistivity tensor, and the experimentally measured values of your resistivity are actually given by these formulas. So as long as you have different resistivities along the one direction and along the two directions, you have a finite transverse resistance measurement in your whole bar, okay? Given also that the angle is not, 0 or 90 degrees. So, sorry, yeah. So as long as sine to theta, because this is sine to theta, is different from 0, then rho xy will be proportional to your resistance anisotropy, okay? To the difference in resistivity between these two directions. Okay, so this measurement at zero magnetic field, and where now I have even corrected for small misalignments between the electrodes and all kinds of geometric factors to make sure we do our as careful estimate of RXY as possible. You can see that it indeed shows this region of high anisotropy. You can even normalize by RXX so that you get a full sense of how strong the anisotropy is. And this anisotropy is of order 50% in this region, okay, here. So it's a very strong anisotropy. It's not a weak effect. Okay? So now, I should also mention, since I mentioned nematicity, anisotropy is now related to nematicity in the normal state, that normal state nematicity evidence has been also seen in recent STM work, okay, by the groups of Eva Andre, Stefan Achberg, and Hypersopathy. So the picture that is emerging from these first two parts of the talk that I mentioned about is the following. So we have a phase diagram, temperature versus doping. I'm showing here the correlated insulated state at 2 holes per mole unit cell, and then we add extra holes, okay? Our superconducting dome seems to have a depletion, which coincides with the region where in the normal state you have anisotropies. You have normal state anisotropy, and that causes a depletion of your superconducting TC. Now, in addition, everywhere in the superconducting dome, we have nematicity. We have an anisotropic response of the superconductivity. And this manifests itself in the behavior of the critical field, critical parallel magnetic field, and also in the behavior of the critical current versus critical magnetic field angle and direction, versus magnetic field, parallel magnetic field angle and direction. Everywhere in this dome, including regions where above there's no nematicity, there is a ellipse, and the rotation axis, the major axis of the ellipse can rotate, smoothly with doping here. However, we see that in this region, when we get to the doping where this region of normal state nematicity is, right, we see a strong rotation, a much faster rotation of the major axis of the ellipse. Okay, so it seems that everywhere in the superconducting state, we have, nematicity. Okay, what sets the direction of this ellipse in this region is not clear. Perhaps the ellipse gets pinned by a small amount of strain. Strain is not responsible for the ellipse itself, but it can locally pin it a little bit or try to pin it to a given angle. Okay. However, as we decrease the doping, as we go towards this region of doping, then this, whatever is setting the normal state anisotropy, seems to be now setting the superconducting state nematicity axis, okay? Because there is a smooth and small angular rotation around here, but then we have a fast rotation axis here. So the rotation axis seems to be pinned here by whatever is setting, or influenced strongly by whatever is setting this normal state nematicity, okay? So this is the picture that is emerging, out of our studies. Now, let me go now to the next part of my talk. And again, Mark, can you remind me, today it's 1 hour, how many?
75 minutes in total, and you still have a little bit more than half an hour.
Okay. And the questions are included in this, or are they afterwards?
No, they come extra.
Okay, good. So I think I have a good amount of time. So let me tell you now about our study of this cascade of phase transitions in Dirac revivals. So this is, again, a different version of the phase diagram that I showed you earlier. This is temperature here. This is filling factor, meaning number of electrons or holes per mole unit cell. You have band insulators at 4 electrons for holes per mole unit cell. At charge neutrality, you have a Dirac semi-metal, in some cases a Dirac insulated state. It's for some groups, they have reported an insulated state at charge neutrality. And then at each integer, you have either a correlated insulator or a correlated semi-metal state, depending again on twist angle parameters and what group and some conditions. And you have strange metal regions, superconducting domes, etc. Okay. Now, let me tell you something that we have found out when we have started to do local probe studies of the thermodynamic properties of the system. Okay. So in particular, the things that I want to tell you about were published very recently in Nature. This was worked on in collaboration with Shahal Ilani's group at the Weizmann Institute. Okay, and this was a paper and a simultaneous paper, back-to-back paper, appeared in the same issue by Ali Yazdani, reporting very similar physics, but using scanning tunneling microscopy. So it was very interesting that with two very different techniques, we were able to reach the same physics and explore the same physics. And this was published on 11 June, which is my June 11, which is my birthday. So I was very happy about this. So the experiments that we did with Shahal are the following. Okay, we measured something called the electronic compressibility. In particular, the thing that we measure is the inverse compressibility. But let me tell you what electronic compressibility is. So electronic compressibility, it tells you how does your charge density, okay, the number of particles in your system change when you change the chemical potential, okay? And in a single particle picture, in single particle physics, this is proportional to the density of states, okay? Now, the thing that we measure in our experiment is inverse compressibility. So we measure d mu dn. So how does the chemical potential of your system change when you add particles to your system, okay? So this is the phenomenology that you can have, and what is the expected inverse compressibility signature, okay? For example, if you have an energy gap, because energy gap means no density of states, you would expect a zero incompressibility and therefore a peak, infinite ideally, but usually a peak or a maximum in the mu dn, okay? A Dirac-like dispersion out of charge neutrality Dirac bands, okay, will lead to a inverse compressibility signal, which goes as 1 over square root of density, okay? So it's a decrease with a specific shape, okay? A decrease of your inverse compressibility. Superconductivity does not manifest itself in the density of states of your system, okay? Superconductivity leads to a gap, but it's a gap that is occurring always at your Fermi level. It's not a gap in the sense of a band gap, it's not a gap, in your regular density of states, okay? So you do not, in the thermodynamic sense, so you do not expect a signal, at least, the first order, okay? So the experiment that we did is the following. So the group of Shahal-Ilani has developed this wonderful technique where he has a scanning single electron transistor that, basically he has a short segment of a carbon nanotube, okay? This carbon nanotube at low temperature acts as a single electron transistor, okay, or as a quantum dot. Basically, it's a very, very sensitive voltage detector, okay? So, electric field detector. So, you can place this carbon nanotube at the apex of a tip, and you can scan this tip, above a device, okay? In this case, a Magic Angle Graphene device, okay? So we can, at the same time, perform transport measurements in this device. So this is a device that we sent to Shahal. We have not characterized it at MIT, so we didn't know whether it was good or bad, or even if it was magic angle, like at all. Basically, a lot of people have asked us for devices, but we don't have enough bandwidth to measure all the devices, characterize them before we ship them. So sometimes we tell people, look, we can give you a device right now, but it's uncharacterized. Do you want it? And Shahal said, sure, send it to us. So it turned out to be, a Magic Angle Graphene device, but it was a little bit disordered, but this doesn't matter too much for Shahal because he can scan and locally check the response in a particular region, So for him, it's actually okay if the twist angle varies substantially because he can just pick whatever region he wants. Anyway, it's not a high quality device from the global transport point of view, but it's good enough that you can measure correlated insulator states at 2 electrons and 2 holes per Moiré unit cell and superconducting domes, okay, for electrons and for holes. This is the transport in log scale versus parallel magnetic field. Now, if you measure now the inverse compressibility d mu dn, okay, this is a particular trace at a given spot. This is a particular trace versus density, okay. These are relatively high temperatures. I'll show you in a moment more detailed data. What you can see, look at the black curve, okay? So again, at 4 electrons and 4 holes per Moiré unit cell, you see a peak, remember, I told you before in the phenomenology, if you have an energy gap, you should have a large peak. So you have this large peak because you have an energy gap there. This is the band insulator. At charge neutrality, you have this peak with a given decay. That's because you have Dirac bands. And Dirac-like dispersion gives a peak with a decay which goes as 1 over square root of density, okay? So this is what you have here, okay? So now, if you integrate the mu dn, you can actually get the actual chemical potential as a function of density, okay? So you can see that the chemical potential for Magic Angle Graphene has these steps at the band insulator. There is because you reach, for example, let's focus on this step here. You reach the top of your conduction band, flat band, then there's a band gap, and then there's the remote band starting. So the chemical potential jumps very fast, jumps at this point that you go from top of conduction band to bottom of the balance of the next balance band, okay, of the next band. So, and the chemical potential exhibits a given behavior also across a charge neutrality point. Now, you can do this, you can, for example, look at this peak in the inverse compressibility as a function of position. So you can take a scan now, this is Y means Y micrometers across a sample, okay? And as a function of density, you look at the scan and you're tracking now this peak is one of these peaks, and you can track it and you can see that, for the first micron, the sample has a given peak at a given density, which at a given gate voltage, which corresponds to a given twist angle. And then this thing shifts sideways, which means the twist angle is changing rapidly in this region, okay? So if you do this in a 2D map, you can actually take again another map, similar to what I showed you yesterday for the case of the scanning nanosquid, where we could get, what is the spatial distribution of the twist angle. You can do it similarly with this technique. You can get spatial maps of what is the twist angle, okay? Now, the sample turned out to be, for the most part, a little bit below the magic angle, but there are also regions closer, deeper into the magic angle, okay? So now, let me show you at lower temperature some more data. Again, the data are now normalized the x-axis to filling factors, so all of these lines are aligned, okay? Even though the twist angle is changing in these different positions, okay? So you can see the actual traces here. You can see, for example, that for theta, for twist angle 0.99 degrees, features are very weak. You have the peaks corresponding to the band insulators. You have the peak corresponding to the charge neutrality point, okay, to the Dirac cones. And then you see some features here, but very weak. But now you take traces at slightly larger angles, 101 degrees, 103, 105. By the time you get to 105, 107, actually to already at 103, okay, you see that a lot is happening, okay? And in particular, a lot is happening for the electrons filling factors. If you get to 1.13 degrees or so, as you can see in this blue trace, you can see that lots of features are happening both for electron and hole filling factors, okay? Now, these are data at finite parallel magnetic field. The phenomenology that I want to tell you about seems to be enhanced when you apply a parallel magnetic field, but I will show you data now in the next slide at zero magnetic field where all of this is present too, okay? Now, what you see here, let's focus, for example, on this 107 degree trace, okay? This turquoise trace, or the one above or the below. What you can see is that starting from charge neutrality, you have this peak with a 1 over square root of density type, okay? Decay of your inverse compressibility, your d mu dn. Then we reach filling factor 1, we reach 1 electron per mole unit cell, and then there is a reset up with a decay again. And then we reach near filling factor 2, and then you go up with a decay again. So you have these asymmetric peaks. Maybe it's easier to see the asymmetry in this 105 degrees or this 113 degrees Okay, of these asymmetric peaks, okay, which are happening, okay, a little bit like sawtooth. Okay, now the other thing that I want to tell you about is you can integrate these curves, and of course you can see that for 0.99 degrees your chemical potential has this square root density dependent, okay, but relatively few features here until you reach the step at filling factor 4. However, for the 105 degree samples, you can see this square root, then another square root, then kind of another step, etc. Okay. As I told you, this is data for another sample. So you can see here that there are data from 2 samples, sample A and sample B. Sample A is the previous one that I mentioned that we sent to Jarillo and that it was not very well characterized. Sample B is actually a much better device that this time we characterized at MIT, and we made sure it was a good device in order to ship to Weizmann, okay? And the phenomenology and the data are much richer, and it has much more uniform regions, large regions with uniform twist angle, okay? Where our colleagues at Weizmann can take detailed measurements. So in that sample B, all of this phenomenology is present even at 0 Tesla, okay? You can see all of these asymmetric sawtooth peaks, okay? Now, what do these peaks mean? How do we interpret this thing, okay? We interpret it, oh, and by the way, let me just mention before I tell you about the interpretation, here you can see this inverse compressibility versus filling factor, and now you can look at the temperature dependence. You know, the maximum temperature, you know, is, for the red curves here in this data is 16 Kelvin, and you can see that you still have these peaks happening, okay, near each integer. So the first thing that I want to say is that this behavior, okay, which as I'm going to tell you in a moment ago is due to phase transitions, is something that occurs at temperature at energy scales well above any superconducting or correlated insulator temperature scale, okay? The superconducting TC for you know, these devices is, you know, a maximum 3 Kelvin. You know, correlated insulator behavior typically is there up to a few Kelvins, maybe 4 or 5 Kelvin, sometimes 10 Kelvin, something like that. You know, this is happening at 16 Kelvin, and in fact, by now we have extra data that this is happening at 30, 40, even 50 Kelvin. Okay, so this is a behavior that happens above any other type of low energy physics that you can measure then at lower temperatures.
Can I ask a question?
Sure.
So it looks like, based on your presentation, you have inhomogeneity of the magic angle in your sample.
We have inhomogeneity of the twist angle. Yes.
Yeah. So of the twist angle. Yeah. Sorry for the mistake. Now, but it depending on what is that twist angle, the incompressibility, how it varies as a function of filling factor looks quite different. So how did you determine, a priori that this is the twist angle that you have, if this plot is quite complicated depending on what is the twist angle?
Yeah, very good. So remember, we're doing our compressibility measurements locally. So I can sit in a given spot in my sample and measure d mu dn versus density for that particular region, okay? So all of these compressibility curves, okay, that look different for different twist angles, they look different for different twist angles. And how am I going to a different twist angle? I'm just changing spatially to a different spot where the twist angle locally is different, okay?
That I understand, but did you know in advance that the compressibility for a particular twist angle would look like this, and then based on the...
No. So there are features in your signal, okay? This is what I try to convey the message here. Where this peak, the band insulator peak, occurs in density, okay, is dependent on the twist angle. Because remember, this peak corresponds to 4 electrons per Moiré unit cell, but the size of the Moiré unit cell depends on the twist angle. So 4 electrons per Moiré unit cell corresponds to different density for different twist angles. And we can see that here. Density is related to the backgate voltage that we apply to our system, which we can control continuously, okay? So you see that this peak is appearing at different backgate voltages in different regions. This means in this region, we have a given twist angle, this region another, this region another, this region another, this region another, okay? So we know in a given region what's the twist angle, and then we can measure the inverse compressibility versus density at that particular location, which tells us for that twist angle, what is the inverse compressibility. Is that clear?
Yeah.
Okay. So, and what I'm trying to tell you here is that this response, which is generic within the magic angle range, okay, in a range of angles around the magic angle, again from 1.1 plus minus 0.1 degree kind of, okay, we see this phenomenology of these asymmetric peaks, okay. In fact, here I forgot to tell you, you can see this trace at 1.31 degrees has no features whatsoever, only the Dirac and the band insulator peaks. There are no sawtooth peaks here, okay? Because 1.31 degrees is beyond the magic angle range. For 0.99 degrees, you see a little bit here, so there's still a little bit there. As I mentioned before, we've seen superconductivity down to 0.95 degrees, So the magic angle range extends from about 0.95 to 1.25 degrees, something like that. You go outside that and you see no features, okay? So this trace is a generic trace at a particular twist angle, okay? And all I'm trying to tell you here is that this behavior persists up to very high, relatively high temperature, okay? Compared to other effects such as superconductivity. Now, how do we interpret these asymmetric peaks in the inverse compressibility, okay? So what happens is the following. Now, let's start from the charge neutrality point, okay? So from zero doping. And now let's look at how, as we add now electrons to our system, where do they go? Remember that I mentioned yesterday that we have 4 flavors in twisted bilayer graphene, okay? Graphene in general. We have spin up and spin down, and valley K prime, okay? This number of 4, that appears, these 4 electrons per Moiré unit cell, etc. All of, 4 appears many times, right? So at charge neutrality, you have these 4 flavors, which correspond to 4 Dirac cones near charge neutrality, okay? Which now, as you add electrons to your system, you want to occupy them, okay? So if there's symmetry, if all of these Dirac cones are symmetric, there's nothing that distinguishes this Dirac cone from this Dirac cone energetically, okay? As you start adding electrons to your system, your chemical potential rises and fills all 4 electrons, all 4 flavors at the same time, okay? So you can see this is schematically depicted here by, you see, we have filled a little bit each of these Dirac cones, okay? We're adding electrons to all 4 flavors at the same time. All 4 flavors get filled at the same time, okay? Now, what seems to happen in the system is that, okay, and this vertical axis here is indicating what is the occupancy of flavor 1, flavor 2, flavor 3, and flavor 4. And you see that we are filling all flavors at the same time with electrons, okay? Now, when we get close to filling factor 1, meaning 1 electron per Moiré unit cell, okay? Now, in principle, if we had just kept filling all 4 flavors at the same time, we would be occupying with 1/4 of an electron per Moiré unit cell each of the flavors. We have 4 flavors, each one 1/4 occupied, gives you a total occupancy of 1 electron per Moiré unit cell. However, that's not what the system does. When the system, when the density of electrons is such that you're close to 1 total electron per Moiré unit cell, 1/4 of an electron per flavor, the system decides to spontaneously fill one flavor completely and empty the other 3 flavors. Okay, so the occupancy of one of the flavors goes rapidly up to 1, and all other 3 flavors get depleted to 0. Okay, this leads to the, and then once this thing leads to 0, okay, and then once this is completely occupied to 1, and these are at 0, now you start filling the other 3 flavors again from charge neutrality. Okay, you start filling these 3 flavors at the same time, but again, once you are close to 2 electrons per Moiré unit cell, or in other words, once you're close to 1/3 filling for each of the 3 remaining flavors, we have 1 already here, and then 1/3 on each of these ones, that means total 2, okay? The system decides again to spontaneously fill an additional flavor, flavor 2 in this case, and empty the other 2 back to charge neutrality. And then this happens again with the last flavor. You fill these 2 flavors. The system then decides to fill 1 flavor and empties the last remaining flavor, which then is filled at the end, okay? So this is what we call a cascade of phase transitions and Dirac revivals. There is a phase transition. The system spontaneously now breaks the symmetry between these flavors. There's a phase transition. I am now going to choose to fill 1 flavor and empty the other 3, okay? And because the other 3 flavors go back to the charge neutrality point, to the Dirac point, we call this a Dirac revival. Now you go again through the process of filling your Dirac cones for the other flavors. And this happens continuously, close to each of these, okay? So this is what this means, okay? Here you're filling from charge neutrality all 4 of your flavors. Something is happening here, okay? The phase transition takes place, then you now rapidly fill 1 of the flavors and the other 3 remain empty, okay? When the system completely completes that process, because 1 of the flavors is completely filled, that one is no longer giving you contribution to the inverse compressibility. Again, think in terms of, again, inverse density of states. You go back to the charge neutrality point here, low density of states, so high inverse density of states. And you start doing this process again, then you repeat it, then you repeat it, and then you go, off you go to 4, okay? So this simple schematic process, okay, seems to account to 0th order for the basic phenomenology that we are seeing in our system. Okay? So which specific flavors get filled depends on a number of things, okay? But we can tell you that at least for filling factor 1, okay, when you fill the first flavor, this is a spin flavor. So there is a magnetization, the system is spin polarized at filling factor 1. Okay, the system decides to choose to put all of the electrons, by the time you reach filling factor 1, puts all of the electrons with the same spin in your magic angle graphene. Okay. What happens at filling factors 2, 3, etc., can be a little bit more complex, and it's still being investigated. Okay. We have new data suggesting that interesting things happen there. So now, this is also telling you something very important, okay? Which is that in this phase diagram that I mentioned earlier, as a function of doping, the ground state of your system is very different before an integer filling, okay, and after an integer filling, okay? Because before you have a state, let's say, which has flavor symmetry, whereas afterwards you have a broken symmetry flavor. And that happens before and after each integer, okay? So this puts some shine some light into one of the puzzles that we already saw in our original 2018 paper, okay, which I mentioned yesterday. So if you look at the Shunikov, at the Landau-Fan diagrams, at the Shunikov-Haas oscillations, okay, you look at the frequency of the Shunikov-Haas, at the effective mass, you look at the Landau-Fan diagrams and the degeneracies, okay. Here I'm plotting from charge neutrality towards holes, okay. As I mentioned yesterday, we saw that the degeneracy of the Landau-Fan diagram seemed to be 4 stemming from charge neutrality, and then also from the remote band, but after filling factor -2, after the correlated insulator state for holes, it seems to be that the degeneracy of the Landau-Fan diagram was 2, okay, which was a little bit puzzling, okay. Also, there seemed to be a reconstruction of your Fermi surface at filling factor -2, okay, for holes. Now, this is now much easier to explain, okay, because as you can see here, after filling factor 2, the same similar story happens for -2. 2 flavors are occupied, and you have 2 flavors unoccupied. So you have now degeneracy of 2 in your Landau levels. You have degeneracy of 4 at the beginning. You have degeneracy of 2 after filling factor 2, okay? So that explains this loss of degeneracy in your Landau-Fan diagram that we already observed in our initial experiments, okay? So this Fermi surface reconstruction was also present in our whole measurement data, okay? This is a figure which is in the supplementary information of our original discovery paper. Okay, it's a little bit complicated. Let me just show you the dark trace, because that's the one at low temperature. So we're measuring the Hall density. Okay? We're doing a Hall effect measurement. We're measuring the Hall density. This Hall density from charge neutrality seems to follow this straight line, which is what you expect based on a capacitance model. But when you reach the correlated insulated state, there is this reset towards smaller Hall density. Okay, it's like the system is resetting back to charge neutrality. Okay, and that thing, that reset, that Fermi surface reconstruction, now we understand it as this phase transition from filling these 4 flavors with an ever increasing Fermi surface to then having a reset back to charge neutrality once this Dirac revival happens. Okay, so these experiments are, have shown a lot of understanding on some of our initial puzzles, in our initial discovery. So in this phase diagram, okay, now we have to add a region of height, which occurs at high temperature, certainly, up to at about 30 Kelvin. Now recent data seems to suggest that we have even this region of favor symmetry broken parent state after each correlated insulated state, at all temperatures below which this interesting physics, correlated physics, coordinated physics, etc., occurs. So this flavor symmetry broken state is a parent state. It's the background on which lower energy physics now happens, okay? So it contains a lot of information for what type of correlated insulated state, what type of superconductor, what are the constraints, what are your elements, where are your electrons, now, the electrons that are participating in the correlated insulated state and superconductivity, etc., out of which flavor symmetry broken parent state they come, okay? So this is something that I wanted to tell you. Now, in this last few minutes of my talk, I think I have only 5 minutes or so, right, Mark? So let me just tell you briefly.
Yeah, 5 to 8 minutes.
Let me just tell you about the strange metal behavior, okay? Now, strange metals, strange metal phase is characterized by strange behavior. That's why the name, okay? Which means many properties are different from what you would expect in a conventional Fermi liquid paradigm. Now, for example, you have resistivity, which is linear in temperatures, all the way to very low temperatures. From very high temperatures to very low temperatures, whereas you expect typically a quadratic behavior at very low temperature. Okay? This occurs in many family of correlated materials, glutenates, cobaltates, samnictites, heavy fermions, cuprates, etc. Is this big region in the phase diagram of the cuprate superconductors, for example. Here's some of the original data where you see the resistivity for some dopings in this region above the superconducting dome, is very linear, okay? In, this heavy fermion, for example, you measure the resistivity versus temperature, you see that it's linear down to the lowest temperature they can measure, okay? This is a very unusual behavior for a Fermi liquid to exhibit. Now, another thing that has been sort of a theme in recent studies of correlated materials is that the slope of this resistivity, when properly normalized, basically the scattering rate, seems to be proportional to temperature with and fundamental constants with a prefactor which is of order 1. Okay, this was, I think, first studied systematically for a variety of materials by the Andy Mackenzie group. More recently, the group of Louis Tyler Ferg has studied this, and this, prefactor of order 1, when the scattering rate satisfies this with a prefactor of order 1, people call this a Planckian bound on the scattering rate. This is a Planckian bound for C equals 1. Okay, and as you can see, it's not a very precise quantization. Let's say 1 plus minus 50%. Okay, but this thing could be in principle 10 to the 3 or 10 to the minus 3, but for many correlated materials happens to be 1 plus minus 0.5, something like that. Okay, so now in this phase diagram of magic angle graphene, okay, I told you there's this region of correlated insulated behavior and nearby superconducting domes. If you take a magic angle graphene device, this one is one which has a relatively high TC, so the system goes superconducting already below a few Kelvin, okay? But if you go above that superconducting incision, you see that the resistivity from then onwards is very linear, okay? And it's very linear up to temperatures. In this case, I only show 25 Kelvin. It's linear quite a bit more in general, but these are extremely high temperatures for the system because remember, this is a very low density superconductor material. So these are temperatures of the order of the Fermi temperature. It's the equivalent of going to several thousand Kelvin to other materials. Okay? You can take now a different device, lead factor at +2 minus delta, and this thing goes linear all the way to almost 0 temperature, okay, right before the superconductivity sets in. This is for one of these small superconducting domes, okay? Now, I'm saying here T coherence. T coherence is the temperature above which the behavior is linear. T coherence in this case is about 0.5 Kelvin, okay? Because TC is, for the 0.2 Kelvin, something like that, for this particular dome. Now, this is something that you can do as a function of density, okay, continuously. So again, it's one of the advantages of our systems. The curves that I show in this diagram, these are for different materials, different crystals. We can do this exact same thing continuously as a function of density in the same device. Okay? This is for 2 different devices, continuously as a function of density from the same device. You can see that above, at low temperatures, superconductivity takes place, correlated insulated behavior, all kinds of things happen, but above a certain temperature for the order of 5 Kelvin or so, you have this linear behavior, and the slope doesn't change dramatically as a function of density. Okay, slope is very similar. You can study the value of this slope as a function of twist angle. 4 angles in the magic angle range, there doesn't seem to be a tremendous difference as a function of twist angle, okay? The resistivity, though, is very high. It's of the order for the maximum values are of the order of several hundred ohms per Kelvin, which is comparable to the Cuprates, or even higher, and several orders of magnitude higher than monolayer graphene, okay? Now, if you go near charge neutrality, okay, so not around the correlated resistance, but near charge neutrality, you see a more standard, more quadratic type of behavior, okay? Now, you can calculate the scattering rate for the system. For some samples, we're able to measure the scattering rate because we can do Shinikoff measurements and look at the temperature dependence. And then we see that this prefactor C is of order 1, between 0.3 and 1.5, okay? Which again means that this system seems to exhibit a linear T resistivity behavior with a close to Planckian dissipation, scattering rate. Now, some people have argued that this linear temperature behavior of the resistivity could be due to various type of phonons, basically acoustic phonons in some cases, other cases Moiré pattern fluctuations, which are also another type of phonons. But although the formulas can capture qualitatively some features, they mostly seem to be off by between 1 and 3 orders of magnitude, okay? And these are relatively simple models as people are making more and more advanced calculations, with more theoretical models, which include Moiré phonons, which actually happen to be gapped, etc. It seems to be harder and harder to reconcile this linear in temperature resistivity behavior with any type of phonon system, okay? In particular, Moiré phonons will give you gaps, which will lead to difference in the slope of this linear resistivity behavior piecewise in different temperature ranges. But you can see that the slope doesn't change at all from close to 0 temperature all the way to temperatures above the Fermi temperature, okay? And that is extremely surprising. And that's, again, something which is typical of the strange metals in correlated materials. Now, some people think that perhaps this linear interior resistivity behavior could be due to electronic origin. For example, higher order Van Hoff singularities have been suggested to be present in Magic Angle Graphene, and there is papers that lead to theory of strange metals from hot fermions, close to systems with Van Hoff singularities. There's a lot of theory about this thing, but we don't know yet. Okay. Now, because I want to end, let me just little summary. I have told you today that there seems to be competition between different orders near integer and filling factors in Magic Angle Graphene. Okay. In particular, there is a region of normal state nematicity or anisotropy in the resistance, which leads to depletion of TC. And everywhere in the superconducting dome, there is a nematic response of the superconductivity. Our local inverse compressibility measurements indicate a cascade of phase transitions and Dirac revivals at each integer filling factor. And we can see that there is a strange metal behavior near the correlated insulator states in Magic Angle Graphene. Now, I should mention that all of this has substantial sensitivity to the precise twist angle, okay? If nothing else, the band structure itself in the theoretical calculations for Magic Angle Graphene is extremely sensitive to twist angle on 0.01 degree twist angle increments, okay? So Magic Angle Graphene is actually a magic angle range. There's a range of magic angles, okay? Or a range of angles for which the magic happens. And the magic can manifest itself quite differently depending on the precise twist angle, okay? And of course, if you have twist angle disorder, chemical potential disorder, they can also lead to different manifestations of different phenomena. And with this, I want to acknowledge my group members. This is the same acknowledgement slides as yesterday. A lot of this work has been done by Yuan, Daniel, and Jane. And today, in particular, I want to acknowledge Shahalilani, the Weissman group, including the theorist, and Alexon Open also in Berlin for the inverse compressibility measurements. And I want to thank you again for your attention these 2 days.
Thank you very much, Pablo, for these many magical results. I'm sure there are a lot of questions now. We already had some during the lecture. Maybe we can start out with a question from Adil that was already asked early on when you were talking about the nematicity. Do you see that both for the filling -2 as well as for +2?
Yes, I haven't shown the data, but we also have strong nematicity in the normal state and in the superconducting state for filling +2. Yeah.
Okay. So Alan, here's a question for you, or not for you, from you. Can you open your mic?
Yeah, Pablo, I was just going to ask, what is the lowest temperature to which the linear and T resistivity has been seen? And so, have you ever looked carefully, in the superconducting dome where you suppress the superconductivity with a weak field?
Yep. So in our devices, the lowest temperature that we have seen superconductivity at zero magnetic linear T resistivity at zero magnetic field is about 0.5 Kelvin for that particular trace that I showed. Okay. I think Dima Efetov has shown at a conference recently, he showed data going down to 0.1 Kelvin linear with the same slope, very similar data to us. down to 0.1 Kelvin. Now, you're right that when you apply a small magnetic field, the region where we see this linear resistivity down to the smallest temperature is the region where we have sort of the lowest, for those samples which, for domes, superconducting domes where we have the smallest TC, we can go to lower temperature and still be linear, right? So when you apply a small magnetic field, then of course you go from superconductivity to a behavior which can be, in some cases, even insulating, okay? Because that Nematicity, that linear resistivity behavior sometimes is most pronounced in this region where we also have this anisotropic state, okay, that competes, this competing order. So it goes from superconducting to insulator. So in between, you can always find a magnetic field for which it looks, pretty much linear all the way to zero at the lowest temperature that we can measure, okay? But sometimes, it goes exactly to zero. Sometimes it's a deviation a little bit depending on that. And I haven't really put a number on what was the lowest temperature for a particularly chosen magnetic field, that the linear behavior would go to.
Okay, got the idea.
In this context, I would like to communicate a question I just received from Andy Millis, who had to leave to host another lecture. He said the characteristic feature of the linear resistivity data is that the offset depends strongly on carrier concentration. Why is this?
Very good observation. So let me see if I can go back. Yes, as you can see, within a superconducting dome, okay, within this range in density spanning the insulative behavior and the superconducting domes on either side, the slope of the linear T resistivity is pretty much the same. What changes a lot is the offset, okay?
Yes.
The extrapolation to zero temperature, okay? So the residual resistivity at zero temperature when you extrapolate to linear. So this is something that we have observed now in many devices. Okay, I'm showing here 2 devices, but we have many devices. We do not know exactly why, okay? This is the case. So in particular, the offset resistivity at zero temperature is not the highest at the correlated insulator state. You can see here, I mean, I'm not sure if it's easy to see, but this green trace, this green region is the middle of the correlated insulator state. So you can see at low temperature, this diverges. It's a little bit hard to see maybe in the contrast. You can see in the zoom, it diverges. But the green trace does not exhibit the largest offset, residual resistivity, right? Nearby regions, this red curve, okay, shows a larger offset resistivity. So that, we don't know why, but, I can tell you that we have seen often, very often, it also happens in this case, that the largest, TC seems to be largest also with the largest residual resistivity. Having large residual resistivity is good for high TC somehow. Okay. That's something that we've noticed in many samples.
Okay.
We don't have a detailed understanding of why, but.
Speaking of TC, here's a question from Adil on the superconducting state. Adil?
Yeah, Pablo, hi. I just was curious, there's also data which says that there's superconducting domes at the other integer fillings. Do you have any idea of the nature of superconductivity there? Maybe it's, I know the big question is it broken time reversal or not? Do you have any idea or any?
Yeah, so I don't know in detail, okay? I can tell you in our devices, we typically see the 4 superconducting domes that I'm labeling here. Some of the people have reported superconducting domes at near other integer factors, the group of Bilayer in particular. We see in all of the domes that we see nematicity in the superconducting state. We always have anisotropies in the response of superconductivity to in-plane parallel magnetic field in the critical current and in the critical field, okay? Now, you look at our posted paper on nematicity, we go there, we did it in collaboration with Rafael Fernandez and Lian Fu. we suggest there, I'm an experimentalist and I like more to go by the data, but let's say our collaborators have written there, okay, that it is extremely rare to have nematicity in the superconducting state, this type of very strong anisotropic response, if you have a plane S-wave order parameter. Mm-hmm. It is very hard to get that. It is much more natural to have this type of anisotropic response and nematicity if you have a non-S-wave order parameter, in particular P-wave or D-wave or combinations of P-wave and D-wave, okay? And we do not know which ones, you can read a little bit there, about, which ones might perhaps be most likely. And, some of these have been suggested by people, D plus IT and different types of D and P-wave superconductivity. But we don't have experimental evidence of the symmetry of the parameter at this moment.
Okay, and here's a question from Ruby, which I also had on my list. Ruby?
Yes, can you hear me now?
Yep.
Yes.
Oh, okay. Actually, my question may sound very stupid to you, but I wonder, how do you measure this twist angle, and how do you control this during device fabrication?
Yeah. So, Ruby, were you present at my lecture yesterday?
No, but I go through it through YouTube video today.
Okay. No, just making sure whether you had seen or not yesterday to make sure how much background I had to give. So let me respond first to the second question. Is the twist angle controlled during device fabrication? Yes. Okay. It would be very hard to randomly hit 1.1 plus minus 0.1 degrees. So we do control it during fabrication. Okay. Now, how do we do it? Okay. We take a graphene sheet, which is a single crystal. We tear it into two pieces, but because two pieces come from the same crystal, the angle between these two pieces is 0. Now we take one of these pieces, rotate it in a controlled way, so we control 1.1 degrees, and then put it on top of the other piece. And that's how we assemble devices with a controlled twist angle, okay? And we can choose whatever angle that we want. And our yield by now is pretty high. I see a question about yield. I'll comment in a second. Now, how do we measure the twist angle? Okay, there are several different ways of measuring, also depending on which type of experiment you're doing. Okay, so scanning nanosquid, scanning SET, the transport. You all can have different ways of measuring the twist angle. For the transport experiments, what we do is the following. We do a 3-step, we do 2 or 3 steps. The first one is get a rough idea what the twist angle is. For that, what we do is we look at what is the peak in resistance due to the insulator state, due to the band insulator.
You mean at the charge neutrality point?
No, not at charge neutrality, the band insulator at 4 electrons per more unit cell, or at 4 holes per more unit cell. Okay? Because we see these big insulator states, high resistance state, big insulator state, and we know it corresponds to that band insulator. We know that that density, that gate voltage, corresponds to 4 electrons per more unit cell. Okay, and because we know what the density is, we know what's the area of the more unit cell, and you know what the area of the more unit cell is, you know what the angle is, what the twist angle is, because the area of the more unit cell depends on the twist angle. Okay, so that's the simplest way of determining the twist angle. Now, that gives you a rough estimate, plus minus 0.1 degrees or something like that.
Okay.
Then we can do measurements in a magnetic field and look at the Landau-Fan diagrams, which give us Shunikov-Dakas oscillations, which go very sharp to a given point. And then we can determine, because we know that that's, let's say, 2 electrons per more unit cell, we can determine very accurately where that point is. So we know the area more accurately, and we know what the twist angle is more accurately. That gives us, on a high quality transport device, that can give us plus minus 0.02 degrees or so. If we do scanning measurements, we can determine this locally and with much higher precision, actually.
Okay. Thanks a lot.
There's a related question by Jonas.
Yeah, thank you for this nice talk. And I remember concerning also the twist angle for those nice images from yesterday, where you determined it with a microsquid, I think, right? And there you defined gradients of the twist angle. And my question is now, how do you define the error of these twist angles? Do you weight it by the area, or?
Okay, so it's different for transport experiments and for the scanning nanosquid techniques and so on. So when you do a transport experiment with the twist angle in the way that I just described, okay? We first look at the band insulator that tells you roughly what the twist angle is. Then we do magnetic field measurements, and the Landau-Fan diagram tells us what the twist angle is. Now, we do a fitting procedure to determine that density at 0 magnetic field to which these lines extrapolate. And you have to determine what these lines that you extrapolate to 0, where are they located? For that, we do a fitting procedure, okay? So basically, for a very high quality device, the Shunikov-Dehas oscillations are very sharp, so you determine the maxima very accurately, and you can extrapolate those lines very accurately. When you have a more disordered device, then those Shunikov-Dehas oscillations are broader. You can determine them less accurately, and you can determine the extrapolation to the density, for the correlated insulator state more poorly. So we do an estimate of how good is our extrapolation based on our fitting procedure, and that leads to the error bar in the twist angle that I have mentioned in some of the transport data. Okay, like in the competing orders data, I told you this is a high quality sample, 109 plus minus 0.02 or plus minus 0.03 degrees. That's what we do. Okay, we do a fitting procedure and we see, what is, we know that it's not 1/15 because that would be way off with respect to the fitting procedure that we're doing. We have some margin there. Now, when we do scanning nanosquid, as I was showing yesterday, or scanning SET, as I was showing today, there you can locally measure spatially the twist angle. So then, over a device, you can say, well, in between your RxX content, for example, we have this region, and what we have is a distribution of twist angles. Okay, you can look at the frequency. Okay, so you have a histogram of twist angles. And then you can show the histogram, or you can say, well, the full width at half maximum of this, Gaussian distribution, if it's Gaussian of twist angle, is 0.02 degrees. So I'm going to say that that's the twist angle of my device. It's a way of characterizing the distribution of twist angles in your device. You can show the distribution. You can give a number for sigma, for full width at half maximum, etc. Yeah.
Okay, thank you.
I think. One question was skipped, which is what is the yield of making successful devices?
Yes. Mm-hmm.
Okay, and how do we cut the graphene? So the yield right now is very high. Okay, now depending on what you mean, of course, by successful device, but let me say successful device is a superconducting device if we're trying to make a superconducting device. Okay, the yield right now is almost 100%. Okay. Let's say up until recently, it was about 50%, but somehow the last cool downs, all of the devices we have measured were superconducting. So the yield is close to 100% in recent cool downs. Historically, the past year and a half has been about 50%. It started with about 30%, then it went to 50%, now it's close to 100%. Now, how do we cut the graphene? So the way we've been doing it until very recently was just tearing it apart. We use a polymer, which I described yesterday in my talk. We come with a polymer, you contact half of the graphene, and then we literally tear it, okay? Now, that tearing process, you wouldn't be surprised if it introduced some disorder, strain, etc. So what we're doing recently, okay, is we take the graphene and we cut it with a laser. Okay, we run a laser through it and cut it. And then we pick up this piece and put it on top of the other piece. Okay, so we no longer tear it, we cut it with a laser, which leads to less strain at the edge. Other groups, I believe, are cutting now with AFM. You can also just cut it with AFM. And it seems to also give good devices. we use laser because we thought laser would be the least amount of disorder introduced at the edge and strain near the edge.
Okay, Young seems to be happy with the answer. And next in line is Yingzheng Gao.
Can you hear me?
Yes.
Yes. Pablo, in the first bar, you showed us in the figure of resistivity against the temperature at 0 Tesla. I see there's a kink in the line. So can you make some comment on it?
Tesla in the first part. Which part do you mean by the first part?
The one you are telling about the competition order.
Okay, let me see if I can go to the specific slide that you mean. Let me see. Do you mean?
Yes, this one.
Okay.
Yeah, in the orange line, I see a kink here at around 1 Kelvin.
You mean this?
Yes, yes, I see. It does not go directly to the superconducting phase, but it seems there's a competition. Do you want to make a comment?
Mm-hmm. So let me see if this one also shows it. Let me see it. You see, it also shows it, right? A little bit.
Yes, a little bit.
Yeah. So we see this quite often, okay? And we are not sure what does it correspond to, but we see it quite often. Now, some people have told us that this is related to having a complex, a multi-component gap. Some people have told us that this has to do with a pseudo gap, so you establish first some sort of pairing before you establish full phase coherence and you go to zero resistance. There are various things that people have told us. We see it quite often. Of course, the simplest explanation would be that you have some inhomogeneity, so some region of your sample is becoming superconducting before the whole sample becomes superconducting, okay? But we see it quite often, and sometimes it's a very pronounced two-step process, so we're not sure.
Yes, and are you working on with this thing?
Sorry?
Are you working on this kind of things recently?
So we're working on many things, as we see these steps and so on, sometimes we try to see if we can correlate it with some of the feature and so on. Right now, it's not obvious to us what to pin it down to. Of course, I have, a lot of interest. The pseudo gap phase of the phase of the Cuprates is a very interesting phase, right? Graphene is a very low density system, so you have to have necessarily fluctuations. A lot of people have told me you must have, there's no way out, a pseudo gap. You have to have some type of pairing before phase coherence takes place, because fluctuations are going to destroy phase coherence before they destroy the pairing. So that's all very appealing, and we'll have some ideas about things to look at in order to see if indeed we have pseudo gap phase. But I can't, I don't have anything to report yet conclusive.
Okay, thank you.
Sticking with this chapter on nematicity, you also have reported on observations that show the nematicity in the normal state. My question is, could that be related to anisotropies of the Fermi surface, to nesting features of the Fermi surface?
Well, if you look at the band structure at the Fermi surface of, I have actually one sort of more theory slide that let me see, what is it? This, for example. So if you look at the electronic structure at the Fermi surfaces, these are what the Fermi surfaces of Magic Angle Graphene look, okay? Mm-hmm. So you see that they have this threefold rotational symmetry for one valley and for the other valley, okay? Mm-hmm. So this nesting of Fermi surfaces, you expect them to have a threefold rotation symmetry. But what we see are ellipses, not threefold rotational symmetric structures, okay? So it means the system is choosing one particular direction, okay? So that is something that when the system has several options to choose, but ends up choosing one particular direction, that means that the response of the system is nematic. That change from C3 symmetry to C2 symmetry, okay?
Yeah,
from
but
if you include both values to C2 symmetry means nematicity. Now, of course, as I mentioned earlier, you could have, for example, strong strain in your system that leads you to choose this particular direction, let's say, okay? And there's a particular nesting for this direction, etc. But it would be very strange that then that direction of your nematic director could slowly vary with charge density as we see that it does, okay?
But couldn't it be that you have a threefold symmetry of threefold degeneracy here? But then, if one of the three possibilities to nest or to develop a symmetry broken state wins over the others, then the other two options are destroyed. I seem to remember that you have similar cases in transition metal dichalcogenides. Mostly you have a threefold symmetry and you see this threefold charge density waves. But I think there are also some cases where you see only a linear charge density wave, although the Fermi surface has a threefold symmetry, because one of the instabilities wins over the other two.
Well, but I mean, but that is precisely what the nematicity does, right? It spontaneously breaks the lattice rotational system in your system. So if you're telling me, is it not that you have three options which are degenerate, but the system chooses one? Yeah, that's exactly what nematicity is.
Yes, yeah. But you have no, I mean, the nematicity you see in the symmetry breaking, but you don't have any order parameter that you can identify yet with this.
No, we don't have, okay? So for example, for the normal state anisotropy that I've shown, okay, the question is it really a nematic order or a smectic order? In the sense that, is it only lattice rotational symmetry that it's broken, okay? Or do you also have translational symmetry broken? Like, for example, stripes, okay? So, you know, that we don't, you know, the more generic feature that we can say is nematicity, but it could be smectic. Maybe we're seeing, you know, we have charge density wave or a stripe order, you know, in that region of the normal state phase of the phase diagram. Okay, so we don't know that.
Okay, thank you. So, are there any further questions from the audience? Let them type their questions, and I will exploit the situation, ask you one more question concerning now these cascading phase transitions that you have discussed. I agree that phenomenologically you can explain the behavior by this refilling of the Dirac cones. From an energy point of view, it doesn't seem to be particularly energy minimizing what is done here. So, what is the actual mechanism that drives these?
Yes.
These fillings.
So this mechanism that I thought comes actually, so our theory colleagues at the Weizmann Institute have actually calculated this, okay? So it is actually, the system really wants to do that. So if you take a simple effective model for the band structure of these flat bands of graphene, you basically have Dirac cones and then the band ends, okay? More realistic models are different, but you can capture the essence, you know, with the simple band model for the flat bands of graphene, and you introduce now Coulomb interactions. You know, it's a critical minimum interaction strength that is needed, but if you are above that minimum interaction strength, this is an actual calculation of the inverse compressibility, the mu dn as a function of filling factor, and you can see that you have this, you know, Dirac behavior, then this phase transition, first of the phase transition occurs here, which leads then to another Dirac revival. Same thing happens here. Depending on whether you have a Lifshitz transition, a first order or a second order phase transition, the details can vary, but you can see that those peaks, okay, those resets happen at each integer filling factor.
So you're saying it's the Coulomb interaction that drives this phase transition?
Yes, yes.
Okay, I see. Okay. And in this context, the curves that you have shown, the inverse compressibility, at some points it seemed to become negative. What does that mean?
Very good, indeed. let me just show this one, for example, right? You see that you have inverse compressibility, which is negative inverse compressibility.
Yeah.
Obviously, you can no longer speak about density of states in single particle density of states in that case, right? You will not have, negative, density of states. Negative inverse compressibility is something that is often seen when you have interactions, okay? So for example, in the fractional quantum Hall regime, you see negative inverse compressibility, okay? So this is something which is characteristic of interactions, and although in this first paper, we didn't point out to this, this is a behavior that now we're exploring in more detail, and we will have more things to say about it soon, okay? But indeed, this negative compressibility has to do with, as I said, this model where you have Coulomb interactions and this band structure is the 0th order model, which explains some of the phenomenology, metric peaks. There are a lot of other things in the phenomenology which have to do, for example, with negative inverse compressibility, with where these peaks exactly occur, etc., for which you have to introduce interactions and long-range part of the Coulomb interaction and other things in a more sophisticated model. And we're working on that now.
Okay, great. Thank you very much. So there don't seem to be any further questions from the audience. I think they're fully impressed by your results, so they don't come up with any further questions. So how are we doing in time? Okay, I think we've had a long discussion round. Thank you very much, Pablo, for answering all the questions and for these beautiful results and this very nice presentation, and yesterday as well. And with that, I can conclude everything for today and hope that we can meet sometime in real life. Okay, thank you very much.
I hope so.
Yeah.
Thank
okay.
You.
Thank you.